Okay, so welcome back. Quick couple of things that I forgot to mention. So when I was talking about the 576 course, the cool thing about that course is that you will have access to GPUs. So we have some local GPUs for that course. Local as in not cloud-based. I'm administering them. So so we have several machines like that. So the assignments there would be very different flavor. You actually will work with. So I was just telling somebody that one of the recent assignments was about translating. So you actually had to get English to your language pairs. So there's some corpus to get sentence pairs, and then you actually train something called a recurrent neural network to do the translation. Learn the parameters of this whatever fancy model to do the translation for any test sentence. Okay, sentences are not the p-dimensional feature vectors that we are talking about. So those are the types of things that you will do in 576. Yeah. Anyway, second thing is if you guys are interested in projects related to some of the material that we're talking about here, projects in terms of like research projects. So it's very different. There's a good chance of failure in the sense that 95 or 99% of the things don't work. So if you're interested, then talk to me offline, and we can discuss. It depends on the skills and what you are interested in, what I'm interested in, but we can figure out something. Third thing, how was the assignment submission last time? I mean, yesterday. Sorry. Was it okay? I mean, there were only 4 questions, mostly applied, right? Oh, was it 5? Okay. So it's more hands-on, but hopefully you're getting, both the flavor of some theory. Of course, some things may be going above your head for now, but it's fine. So hopefully getting flavor of both practice and theory. Okay, so let's actually switch gears. So I'm going to spend, so today is going to be just a quick warm-up of unsupervised learning. So I keep asking this poll every class. So how many of you have already taken 572? How many of you have not taken 572, I guess?
I'm taking it now.
You're taking it now? So simultaneously, who's taking it? So a couple of people, 4 or 5 people. And some of you have not taken 572, right? That's fine. So because people have taken 572 must have already seen some of the unsupervised learning methods as well. So for you guys, there has to be a review. So today we're going to look at one method called association rules or frequent item set mining, actually. So unsupervised learning, okay, as the name implies, there are no labels. Okay, so there are no y's, yi or gi's here. There's only xi's. Okay, so that's our primary interest, and we've actually already seen one example model here when we were talking about maximum likelihood estimation. So maximum likelihood estimation anyways, you can do it unsupervised as well. If you're estimating the mean and variance of a normal distribution, there is no labels here. You just have data. You're estimating the mean and variance, right? It's just estimation. We've also seen, I mean, these are algorithms or frameworks. We have also seen EM. But in terms of models, we have also seen Gaussian mixture models. Okay. So let me come back to that pretty soon. That's an example of unsupervised learning model. Okay. So what is the goal here? There is no, I guess, goal is exploratory. So no objective measure of success. I mean, you can define some objective and then maybe you can define success, claim success. But unlike supervised learning where, somebody can, your manager can tell you, oh, this is a loss function that you want to minimize for, your model has to work accurately for. I can hold out data and test how well you have prepared a supervised learning model. In exploratory analysis, there is no such benchmark, right? You have to, it's in the, you just have to interpret the results to kind of figure out whether you are successful in exploring your data well, obtaining some patterns, some information from your data or not. Okay, so there's no objective measure of success. Okay, unless you arbitrarily define some measure of success, and then that's completely different. And exploratory. So I just want to explore the data. I have a bunch of data points. What is the goal? The goal is to, at least in this class, it's going to be trying to understand P of x. I mean, this is not always the case, but for us, we've been, the first few lectures we've just been talking about the joint distribution between x and y. Although I guess in SVMs we did not talk about joint distribution, but we'll come back to this, like interpretation that whatever we're trying to do is essentially about understanding this distribution on x. Okay, and Gaussian mixture models were one example of that, right? I mean, we assume that x's are observations, but there are actually latent or missing observations which would tell me that this x belong to a certain component of the Gaussian mixture or some other component of Gaussian mixture. Think of two Gaussian mixtures. If I only look at a joint distribution which looks like this, two modes, right? Some histogram like this, x's are what I observe, but in Gaussian mixture model there was also this latent or unobserved variable for each observation, which would say which component of the Gaussian, which Gaussian component did it come from. Okay, did that observation come from? That's missing. Okay, but ultimately we want to understand P of x. Okay, that's the goal. That's what I mean by exploratory. So what can you understand about P of x? You can understand about modes, as in peaks, the hills. Like for example, chop this off. Maybe I want to know what region of the x space is the probability of the x value taking high. Okay, understand the modes. For example, understand the support high density region, which is essentially the modes, and things like correlations and so on. So whether the first subset of features are related to the second subset of features, are they simultaneously high or low, and things of that nature. Okay, so all sorts of functions of these this distribution P of x, okay, or this joint distribution P of x. And some methods that we've already seen. Actually, did we see? Oh no, some methods we will see in the next 2-3 lectures is going to be principal components. Okay, so here we think that our data x has some redundancy, and hopefully we can get rid of that redundancy. Okay, so it's essentially falls under the umbrella of dimensionality reduction. Okay, that's one thing. We look at clustering. There are a few other things that we can also see which are about dimensional reduction, but I don't want to write it. So there's clustering, where we again want to understand the modes of my data. Okay, basically clusters, you can think of them as high probability regions of my distribution x. Okay, and we'll see both k-means and k-medioids, variances of k-means. We'll also look at spectral clustering. Okay, and there are many methods because as I said, the goal is not clear. I mean, even if the goal was clear, there are many methods, which is supervised learning. So we'll look at spectral clustering, which is going to involve something interesting called a graph Laplacian. And the topic of today is association rules. Association rules themselves, once you have rules, you can actually do supervised learning. So what I care about is what are called frequent item sets. Okay, and I'll spend the next half an hour talking about frequent item sets. So coming back to clustering, k-means and spectral clustering is what we'll see in subsequent lectures. But we've already seen GMM. Okay, Gaussian mixture model. Okay, we've already seen GMM, as in at least fitting the parameters. If you have mixture of two Gaussians, I need to find out two means, two variances, and the mixture components. Right, those are the parameters in when we're thinking about EM. So once I have a GMM model, let's say I somehow trained it using EM, which was subject several lectures ago, then I'll have a mu1, mu2, sigma1, sigma2, and some mixture proportion, some pi or something. Pi is a symbol here. So let's say I have this model. So from EM using data, I went using this algorithm, I got these parameters. Now for any new observation, I can actually find the probability of that observation x is equal to x given the first cluster, given the first component, I guess first component, by which I mean I know in the first component what the Gaussian parameters are. It's a Gaussian distribution with some mean and some variance, which is mu1 and sigma 1. Okay, so I can find the probability of x. I can also find the probability of x is equal to x given the second component, right? There are two numbers now. So given an x, I could find out what's the probability that it comes from the first component, what's the probability it comes from the second component. Whichever number is highest, that's the component that it belongs to. So I clustered a new point. Okay, so that's what I mean by GMM was already a clustering model. It was if you had multiple modes in your data set, it's like it's fitting a Gaussian at each one of them, and therefore it's like a cluster. You can chop the Gaussians from the top view, you get some concentric circles, and they're like clusters. Okay. Anyway, so that's any questions about this part? Okay, so now let's look at association rules. So association rules are an interesting technique, so which were developed in mid-90s and quite popular, and probably are still quite popular because they are so kind of very interpretable and easy, like decision trees. So what's the goal? So let's think of binary data set. It's not binary classification, but binary data set, by which I mean that every feature is just binary. Okay, so I have x1 to xp, each xi is binary, it takes a value 0 or 1. Okay, just the on or off type of a feature. And the typical example that most of you have already heard of is retail data set, where people purchase or not purchase something. So if you look at their transaction record, maybe they have purchased item 1, 2, and 3 and not purchased item 4, 5, and 6. Okay, so then you'll have a entry corresponding to them, maybe just the purchase items, but then you will also know that they did not purchase 100 different things. So you'll have binary feature vector for that transaction. Okay, and what we want to do is find joint values of subsets of x. Okay, this is x. X has p dimensions, p features. Find joint values of the subsets, okay, that appeared, I guess, most frequently in the data set. Okay, so this is what I mean by high probability, I guess, events or high probability values. So basically these are binary values, binary valued features. So I'm just asking, okay, there must be some setting, some assignment of these random variables. I'm just asking, okay, there are really some settings which will have high probability mass. Can you find them? Can you find them from the data? Okay, your data is just records observations of these x features. Okay, is the objective goal clear? Okay, and so this English statement essentially, can be written as probability of okay, let me write it properly. Let S I be a subset of 0, 1. Okay, because xi's take value 0 or 1, I'm just saying, okay, let me take Si, which is a subset of this set 0 or 1. So what are the possible subsets? 0 or 1 or 0 and 1 or nothing, right? Nothing is empty set. Okay, these are the possible subsets. So all I'm saying is, can you find S1 to, let's call it S1 to SP such that the probability of the intersection of I is equal to 1 to P of xi belonging to the set xi, okay, intersection of this is high. It's just a way to say I have some preferred values, not preferred values, I have some, this is a way to say that SIs are subsets of 0 comma 1. Okay, I want to find one subset per coordinate, okay, such that xi taking the values in that subset is as high as possible. It's the same thing as the English statement. Find values of these x values which have the high, which occur more frequently. Okay, is this notation clear? Okay. And actually the reason why I introduced this notation is you don't have to have binary actually. So although I'm gonna, for the next slide onwards, I'm gonna talk about binary data, I can think of, I just need qualitative variables, which means that I just need categorical variable. So instead of 0 1, it could be 0 1 3 4 5 whatever, 100 different numbers. Maybe each one has different sizes actually. Like one variable is binary, the second variable has 10 values, the third variable is 13 values, whatever. So I can still find these probabilities of these events. Okay, I can define the set. So this is richer than the binary association rule that you might have seen, association rules, I guess, treatment you might have seen in the in some other class. Okay, but this is general. This is the most general idea. Okay, now let's come back to the binary case. So in particular, what we're gonna care about in the binary case, we don't care about xi taking a value 0. Okay, we only care about these sets where the sets are actually sets of, which include the entry 1. Okay, therefore the probability in the previous slide is the same as probability or product in k in some set script k of xk is equal to 1. Okay, so what is the set script k? So now we change the notation where we are saying that find me a subset. So there is p values, right? P values, p cross 1. Find me a subset, maybe this one, and this one, 1 2 3 and 4. So this is a subset, let's call this k. Okay, script k, the set of indices 1 3 and 4, and over the 1 3 and 4 indices x values. Okay, pick the x values, multiply them together, they all evaluate to 1. And this is, since it's binary data, all I'm saying is all of them actually simultaneously take value 1. Okay, that's a specific example in the binary case. Okay, so I just want to find the set, for example, an example of set like this, such that this probability is high. Okay, so this, at least if you did not understand the notation from previous slide, this slide should make sense, because this is saying binary data, all values are binary, and whichever, so what subset of these xi's, all take values 1 simultaneously in my data. It's like what products were purchased together, because if they're purchased, there is a value of 1 in their entry in that observation. So which values are purchased together, okay, more frequently. And yeah, so this guy, you can estimate it from data. And this guy, the estimate is called the support of k. Okay, so support of this script, I guess, k, and it's nothing but count. You have n observations, let's say 1 by n, the usual n observations. You just count over all observations I is equal to 1 to n. How many times did k in script k? How many times did the ith observation, how many times did the ith observation have this all the values 1 or not, right? So this is nothing but same thing over here. Here there's a capital X, which is a variable, Here I just have the ith observation. So for every observation, just multiply those corresponding entries in the set K. If they are 1, then you count as in your numerator, and that's called the support of this set. Okay. Now what we're going to do is two things. The first thing I'll do in a reverse order. First thing I'll say I'll discuss what if you have already found a bunch of these Ks which have enough support. Okay. So let's say I have these script K sets J such that support, let me just use the notation support of script K J is high, by which I mean, let's say something like greater than 0.1. Okay. Let's say I have this collection of sets. Okay. What can we do with this? I'm going to talk about that for the next couple of minutes, and then I'll talk about how to compute these guys. And there's a famous algorithm from 25-30 years ago called a priori algorithm, and we'll just discuss how to compute these guys. So let's say you computed these guys. What can you do with them? Right. One is, of course, as I said, the goal was exploration. So you can look at these high probability, I guess, sets and see what items are co-purchased. Okay, maybe milk is co-purchased with bread a lot. That is kind of obvious. Maybe it is, you get it from your data. Maybe your audience is different, so they don't purchase milk with bread. So that's also something you will find. Okay. Yeah, actually, in fact, you can segment your customers based on demographics, and for each demographic, you can actually find whether they have the same co-purchasing pattern or not, for example. Okay. But there's one application that so these are called frequent item sets, because they're frequent enough in our data. Okay, very natural naming. Now with these item sets, you can actually do a few things. You can actually do classification, you can actually do recommendation, and various other things. So to do them, you're going to convert them into rules. Okay, and that's where the association rules comes and the naming comes from. Association, because you're associating features, coordinates of features with each other. Okay, how am I going to generate a rule? So I have this set K, let's say 1, 3, and 4. That was the example from the previous slide, right? I said so let's say this is a set. Then what you're going to do is look at all subsets of this set. Okay, let's say this is one of the KJ. Script KJ is this K1. Let's say K1 knows this. Then you look at sets 1. I mean partition. So basically, you look at all partitions of this set. Okay, partition just means break the set into parts. In fact, we'll look at 2 parts. So I'll break it into 1, 3, and 4. Maybe 1 and 3, 1 and 4, 3 and 4. Okay, 1 and 4 and 3 over here, 4 over here, and there are actually a few more. Okay, you make these partitions. I mean, these are not the only ones. There are a few more, and then you kind of pick those partitions. Okay, so let's say this is an example of a partition. From this I'm going to define a candidate rule, and the rule is going to be if the left hand side, or the what is called the antecedent, then the right hand side, which is called the, what is it called, I don't know, consequent. Okay, so it's a rule. Okay, this is a rule. Okay, so I had a frequent item set candidate, let's say 1, 3, and 4. Okay, coordinate 1, 3, and 4, like item 1, 3, and 4. I broke it into one partition, one example partition. There could be many partitions, and each partition will give me what is called a candidate rule. Okay, the rule is if item 1 was bought, then recommend item 3 and 4, for example. Okay, that's a very simple recommendation, right? So this is called a rule, and you can assess the quality of a rule as well. Just like we preferred those frequent item sets which had enough support, right? So similarly, we can prefer those rules which have some high quality metric as well. Okay, one example metric is you can pick rules with high confidence. Okay, what do I mean by that? So I had this k1 from which I created a left hand side and right hand side. Let's call it P implies Q. Okay, I mean, let's call this a rule. Basically, if P, as in if item 1 was bought, maybe bread, then recommend milk and something else. Okay, that's a rule. Now I want rules with high confidence, by which I mean, so I'm going to attribute a metric to a rule, a metric as in like a score for a rule, which is the follows, which is going to just be a function of the supports. So the score is going to be the support of P union Q. Okay, which is P union Q is nothing but k1 in this case, right? The union of the, like 1 union 3 comma 4 is just k1. K1 was 1, 3 and 4, right? Divided by the support of P. Okay, it's just the support of the left hand side of the rule. Okay, so this looks like an arbitrary scoring. So what is it? It's actually trying to find the conditional probability of, in this case, let's say k1 was 1, 3 and 4, right? Conditional probability of x3 is equal to 1, x4 is equal to 1, given x1 is equal to 1. Okay, that's what this is approximating. So this thing is called confidence. Okay, and that's approximating this probability. And this probability is nothing but if you know the joint distribution between all the variables, this is just a function of those joint distribution, right? Because you can, once you know the joint distribution, you can compute marginal, you can compute conditionals, all that we discussed several times. So confidence is nothing but a proxy for an estimate from the data for something like this, which is a property of the joint distribution. Okay, it's just saying of all the situations where x1 was 1, tell me what the probability of x3 being 1 and x4 being 1 is true. Okay, so high confidence just means that when x1 is 1, x3 and x4 are also simultaneously 1. Okay, this is all correlation, by the way. There is no causal interpretation here. Okay, so anyway, so this is called a confidence, and you can have rules with confidences. You can get rules if you have frequent item sets. You can look at all sorts of partitions for each frequent item set, pick the rules which have the high enough confidence, and then there are some, hopefully there are some high quality rules with which you can just understand them, of course, explore, and you can use them for recommendations or for making classification. Okay, so what's the application for classification? You can actually order the rules. Okay, rules, if rules are like if A then B, right? If P then Q, you can order the rules such that they minimize some misclassification error. So that's something that people have done a long time ago. And actually, I had some work a couple of years ago about using association rules. So once you've already gotten these rules, how to use the rules to make recommendations in a privacy preserving manner. So you intersect data mining, or basically unsupervised learning, with cryptography. So basically something called Oblivious Transfer is a technique to have an interaction between a client, for example, your mobile device, and the server, where the mobile device doesn't reveal what was queried from the server. Okay, or basically the server doesn't know what was queried. Like, of course, this doesn't it involves basically several queries such that the server doesn't know what's happening. Okay, so it's a cryptographic based protocol to do recommendations where there is some privacy of the user is preserved. Okay, anyway, yeah. So now let me spend the next 5 minutes about how to compute the frequent item sets. Any questions about the rules? Yeah. So how to get the set kj such that the support of script kj is greater than, let's say, 0.01. I mean, that 0.01 is something you can change. So one example algorithm. There are many algorithms to do this, and of course sometimes getting you also change the objective. You don't really care about item sets or these subsets with the high support. You also care about a lot of other things, okay, maybe diverse subsets and things like that. Then you can have different criteria. So the algorithm that we're going to look at is called a priori. It's actually an exponential time algorithm in the sense that it will take a long time if you in the worst case, okay. So in the worst case, in the sense that what is your input here? Input is data set, right? So a data set can have arbitrary values of ones and zeros in the n observations that you have, n locations. So different data types will have different ones and zeros, right, patterns. So there could be some data sets for which a priori will take a long time. Exponential time just means that takes time exponential in the dimension or the number of observations, whichever depends. Actually, in this case, I don't remember, but so that's what it means. So the algorithm can take a long time to compute these high support rules. Okay, so high support frequent item sets. Now that's fine. So let's look at what the idea is. The idea is that the key idea is that core idea is that okay, I didn't write it properly, but if script k1 is a subset of script k2, then the support of script k1 is greater than or equal to support of script k2. Okay, I mean, this is kind of simple, right? So if what is the support of purchasing a single item, it has to be at least the support of purchasing an item with something else, right? So this is a simple idea, but you can actually use this idea in your algorithm, which is going to work in rounds. Okay, rounds as in just phases. So it's going to work in phases. So in each phase is going to compute certain size frequent item sets. Okay, so in the first round, so I'm going to describe each round. So the first round, initial round, it's going to compute a single item sets. Okay, single item sets. So it's only going to compute case, the sets such that the support of single items is at least greater than whatever 0.1. Okay, so single items, just bread. What's the probability of bread equal to 1? That's easy, right? You just look at one column, n observations, one column, and maybe 30% of the data has ones in that column and everything else 0. Then that probability is 0.3, right? 30% is ones, and that's it. So 0.3 is greater than 0.1, so that you include as your that you keep. So if greater than the threshold 0.01, keep. Okay, you keep that set. So you keep many such single item sets. Okay, now in the second round, okay, you form pairs from the selected single item sets from the previous round, from previous. Okay, so basically all pairs of sets that you can form from the sets that you've already chosen in the first round. Okay, and so you have pairs. So second round, in the first round we have single items. In the second round we have two sized item sets. In the third round we'll have three sized item sets, and so on. So therefore the number of rounds is going to be p, where we'll have p sized items potentially. So we'll form pairs of items only from the selected items from the previous round, and then again we'll check whether the probability or the support of that kj, maybe it's I comma j or some pair of indices, is greater than threshold, right? And we'll discard the pairs which don't cross this threshold. So that's kind of simple. And then you do the same. So in nth round, form m-sized sets from previous m-1 sized sets, in the sense that if you're gonna pick an m-sized set, then hopefully all its m-1 subsets are there in the previous round, have not been eliminated in the previous round. So for example, if in the mth round you're looking at 5 1 okay 1 5 9 and 11, so this is a set, maybe number of features is greater than 11, then hopefully in the previous round, in the mth round, so m-1 round, m-1 round, you had 1 5 9 1 5 11 1 9 11 5 9 11 and so on. So hopefully all these sets were still remaining in the previous round. Only then you will consider this set and compute its support in the current round. Okay, and if its support is greater or lesser, then you will keep it or not keep it. Okay, so this is a very bottoms up approach. So you're constructing from bottom layer all the way to the top layer, and that's it. So these the things that remained in each round, those are your frequent item sets. Okay, so that's the algorithmic procedure. It's just a very simple iterative procedure where you're only combining the sets which are already there from the previous round. Okay, so any questions about this part?
So if in the m-1th round, one of the three m-1 sized set is absent.
Yeah,
so
it's not 3, it has to be 6 or something. I don't know. Yeah.
So
4 choose 3.
For example, if the 1 5 11 is not there, it doesn't cross the threshold.
Yeah.
So if we will be going to the mth round to calculate, or
no, we will not.
We will not.
Yeah. So because if one subset is not having enough support, then this thing will not have enough support. We just discussed that in the so if support of this guy, smaller set is small,
Yes.
then the support of the bigger set is going to be even smaller. That's the idea. I mean, it's a simple idea actually, but any questions about a priori? So this is one way. As I said, it may take a long time. There are already like good packages in R, Python. There's Java-based thing as well to compute these. It's actually a very good first tool for exploratory analysis, especially if you have categorical data. Okay, I mean the other thing that you could do is always clustering and stuff. Categorical data and PCA you can still do, but I think this to get some patterns or some ideas of what's co-occurring would be a good first cut. Okay. So we are pretty much at the end of this lecture. I want to give you another example of application of association rules, or not association rules, but frequent item sets. So there's another research thread which I was looking at. Okay, it's about the problem is called assortment planning. Okay, assortment planning is a problem in operations management, or basically revenue management. And there, basically, you are trying to figure out what is the best set of things to show to a customer to maximize your revenue. So you may have an inventory of 100 different products, 1,000 different products, but you may have limited shelf space. Okay, if you're a brick and mortar store, or you may have, if it's an online store, then you may have a limited, page size to show a few things, in the first impression when they open the page, right? So in that limited space, you can't really show all your 1,000 products. So you may want to show the top 6 or whatever, top 6 products or top 7 products. What are the top 6 or 7 products that you want to show? Okay, that depends on how you model your customer behavior. Okay, so there has to be a behavior model for how the customer observes your 6 products and chooses something. Okay, of course, if the customer chooses a product irrespective of what else is being shown, then it's like some sort of a easier problem, because it doesn't matter what product is placed next to another product. Okay, but when there is neighborhood effect, as in when a product is placed among other more beautiful products, then its sales decreases, or its sales increases when it's placed next to some other products. Then you have to be careful about what to place next to each other. Okay, so that's called an assortment. Okay, this the 6 products that you want to show on the shelf or online is called an assortment. And you can have various parametric models, just like what we did, mapping between features to predictions, right? Features to labels. You can have a parametric model given a customer feature. You can tell like what is their propensity to pick the first product, what is the propensity for them to pick the first 2 products, not first 2, but like any subset of products given the 6 products. Okay, there are different models like that where you can fit the parameters using EM, MLE, supervised learning, whatever. So once you fit that model, then you also have to optimize for what is the best set assortment that you can show. Okay, that's the optimization step. Now, how is it related to association rules or frequent item sets? Is that you can bias yourself towards products that have actually already been co-purchased highly frequently enough. So you don't have to search over all combinations of products to figure out what is the best assortment to show. You already know from historical transaction data that maybe there are some products which are highly selling and also highly selling in terms of co-occurrence, in the sense that product A and product B were highly selling and co-occurring. That information can be used while choosing your optimal assortment. Okay, so basically I want to give an example of where frequent item sets can also be used for decision making. Okay, especially for revenue management. So you chose your correct assortment. Hopefully you can make more revenue than choosing some incorrect choice, especially when they're neighborhood effects. Okay, and for that you have to your solution is a set, an assortment, and sets are natural candidates here, right? So we are mining sets from data. So there's a link between what we're mining and what we want to do for our revenues. Okay, anyway, so that's it for today. If you have questions, come by.